Hi everyone, thanks for being here. Today I'd like to introduce our work, TinMan, which is a system that aims to protect confidential data on mobile platform. This work is done with my colleagues in iPads, Shanghai Jiao Tong University. Our motivation comes from following two facts. The mobile devices are full of user secrets. For example, web account, password, bank account, credit card numbers, etc. However, the mobile devices are very easy to get attacked, either software attack, hardware attack, or other many kinds of attacks. So the question is, how to protect secret data on the phone? First, let's see how many ways an attacker can steal your secret on your phone. An attacker can simply install a keylogger on your phone and steal every input, all of your input. Actually, you can buy that service on eBay. Or he can just install a malware to lure the user to enter the password. A typical malicious application can lurk in background, waiting for some application, for example, the Facebook application to launch. And when the Facebook application starts, the malicious application will get activated and make itself cover the real UI, so the user will enter the password to a wrong place. Or the attacker can use rootkit and just scan the memory for any plain text. This text is simple but effective, since the memory does contain many secrets. Here's a table from CleanOS OSDR draft paper. It shows that many popular applications will leave residue of critical data in memory for a long time. For example, the Android's default email application will have plain text of password in RAM 10 minutes after login. Or the attacker may even steal your password from screen. As we all know, on iOS system, once you enter a password, the last character will be displayed for a second. So if the attacker can access the frame buffer, he can just get a password. Or codeboot attack is also possible on mobile devices. An even more sophisticated attack is to use motion detector to guess the user's PIN code, and just by learning the relationship between the PIN and the user's input when just click the screen. I can go on if time allows, but that will take me another 3 days, so I just stop here. So we get to the conclusion, it's very hard to protect critical data on mobile devices. The data residue might be in many locations in the system. For example, freed but not zeroed memory pages or blocks, socket buffer, SSL buffer, swap file, or even screen buffers. Just deleting the critical data by application is far from enough, since the OS may copy data without application's awareness, and some data may even be recovered after being deleted. And it's hard to be sure that no residue on the devices. Just by searching the memory dump is not enough, because the secret data may be in very many kinds, different types in the system. So we just think our question again: how to protect secret data on the phone? Our idea is, how about no secret on a phone? So we will have nothing to protect. This is the idea of TinMan, and we need to answer following 4 questions: which data protect? How to ensure no critical data on device, how to be transparent to application and web servers, and how to enforce access control of this critical data. First question. There are many different types of data in system, and the most critical part, such as the password, credit card numbers, they are usually too dangerous to be displayed. And we call this data the confidential record, short as core. It's just this part. And in this work, we are focusing on this part instead of all the private data. So cores are not email contents, call logs, SMS, or things like that. This data we just called private data. We have some observations that in the system, there are typically a few cores, but these cores are super critical. So in order to achieve no core on a device, we introduce a trusted node to store the cores. The trusted node can be a cloud, a server in company, a PC at home. The local device only stores a placeholder of the core, and the plain text of the core is stored on trusted node. All the accesses to the cores are done by trusted node. Otherwise, there will be plain text on the device. The basic idea is to adopt security-oriented offloading. When an application runs on phone needs to access the core, it will be migrated entirely to the trusted node to access the core. After that, it will be migrated back to the phone. Our offloading engine is based on commit. Let me have a brief introduction to commit. Commit is a system that uses DSM to sync memory between both sides. So both the device and trusted node can run exactly the same application, and the application can be offloaded to another site at any instruction. But TinMan is security-oriented offloading, so no sync for cores, and the offloading is triggered only when a placeholder is accessed. A major challenge is that the commit is an application-level offloading engine. However, since TinMan needs to send core data by the trusted node to the server, it also needs multiple level offloading, including SSL level and TCP level, in order to support I/O operations on the trusted node. However, the SSL protocol forbids us to send core data from the trusted node. For example, if we run an application on the mobile phone, it will have an SSL connection with the web server. And once it needs to send the password to the web server, And once it needs to send password to the web server, it will be migrated to trusted node. However, if the trusted node sends the core data, it will be considered as a man-in-the-middle attack. In order to solve this problem, we first divide the sent data into different SSL records. This is supported by the SSL protocol, so no change will be needed on the web server. And for any data before the core data, we can send directly from the phone to the server. And once it needs to send core data, it will be migrated to the trusted node, and the SSL state will be synced from the phone to the trusted node. So the trusted node will send the data on behalf of the phone. After that, the application will be migrated back to the phone, as well as all the SSL state, to finish all the data rest. However, we met another problem named the implicit IV problem. Because if SSL uses CBC encryption, it typically uses the last ciphertext of the block as the initial vector for the next block. And if you want to, this is known as the implicit IV and is used before TLS 1.1. So consider this situation. If we send data first on client, which is a phone, and then we migrate to the trusted node, and then migrate back, then the IV, which is the ciphertext of the last block, and the ciphertext of the plaintext of the ciphertext on the trusted node will be sent back to the client. But using this equation, the client can just get the plaintext of the trusted node through this IV. In order to solve this problem, we need to enforce the application to use explicit IV, which is getting started to use from TLS 1.1. In explicit IV, no IV is needed between different SSL records. For TCP offloading, we need to, and one naive way is to change the TCP IP stack, similar as the SSL application, for both sides to sync the TCP state. However, this application will be very complex. We use a new solution named payload replacement. For all the data without the core, we just send from the phone to the web server. And once the phone needs to send the core data, it will send some placeholder, which is garbage data, to the web server. In this case, a TinMan will redirect the package containing placeholder to trusted node. And once the trusted node gets the package, it will keep the TCP header and replace the payload with core data, and then send the package to the web server. So From the web server's perspective, it will get package as if it is sent by phone. No need to change. In order to be transparent to applications and web servers, we use tainting to track the data flow of cores and placeholders. On the device, we track the placeholders in order to trigger offloading. And on the trusted node, we track the data proportion of the cores. Both the tainting and migration are transparent to applications. And we also do optimization named asymmetric tainting. We have such observation. The phone side has to enable tainting to track the placeholders. However, since the phone only needs to know when a placeholder is accessed, a full-fledged taint mechanism is not necessary. Our optimizations work like following. We classify tainting into 4 types, from heap to stack, stack to heap, and stack to stack. And we find that we only need to adopt 2 types of tainting on the client side, which is heap to stack and heap to heap. More details can be found in the paper. The last question is how to enforce access control of the cores. Because a malicious device can use phishing to make the user to send a placeholder to a malicious site, or it can migrate a malicious application to the trusted node to access the core. Our solution is to introduce 2 whitelists. The first is application whitelist, which control which application can access which core, and website whitelist, which control which site can a core be sent to. And we can also adopt other trusted site security enhancements. For example, we can revoke access while device is stolen or lost, or we can adopt more sophisticated mechanisms to detect anomaly access pattern. Here is one case study. We protect password in BankDroid, which is a very popular bank management application on Android. As we can see, instead of typing your password into this widget, we just select the password. Actually, the password will never be exist on the device. In order to initialize the password, we need the initialization of password is on trusted node through the secure channel, and it will synchronize only descriptions to device. So the user select password instead of typing them, and the password and its placeholder are tainted. The device only has a placeholder, and the entire login process should be offloaded to a server, and the password will never appear on the phone. In order to evaluate our performance, we have following 3 questions. How much overhead does TinMan incur? How much extra energy does TinMan cost? And how much extra traffic does TinMan bring? We first use Haibing mark as our benchmark. The average performance overhead is less than 10%. As we can see, some optimization of the string operations enabled in the original Android system are disabled. So the string benchmark is not that good. And the ratio of heap to stack operation is very high in this benchmark. That's the reason why the performance is low. And we then measure the end-to-end latency of logging for different applications after warm up, because the first time we need to transfer the entire binary of the application to a server. As we can see, the overhead is less than 3.1 seconds for all these cases. We also measure the percentage of offloaded code in the total number of method invocation. There is very few percentage of code offloaded, less than 5%. And the synchronization times are also very small. We also measure network traffic overhead. If we log into PayPal 10 times a day, it will cost 8 megabytes extra network per month. In order to measure battery consumption, we run 2 different scenarios. The first scenario, we consecutively log into PayPal for 30 minutes. The battery drops from 93% to 91%. And in the second scenario, we run Angry Bird, Wikipedia, and playing video, each for 10 minutes. And we can see the battery is similar. Our work is based on many existing researchers, including Paranoid, CleanOS, Commit, and others. The major difference of TinMan is that we assume no plaintext of confidential data from the beginning to ensure nothing to lose. Here comes to our conclusion. Our motivation is to protect confidential data on mobile devices. The idea is a design showing no confidential data on the phone. Our design uses offload to access the confidential data to a trusted node and use tainting to trigger the offloading. We implement a system-level security-oriented offloading that considers network state to keep transparent to applications. And the overhead of latency, power, and network traffic are modest. Thanks for listening, and I'm ready to take questions.
Questions?
Cristiano Giuffrida from Amsterdam.
Hi.
Cool work, thank you. I'm curious, do you deal with implicit flows?
I'm sorry?
I'm curious if you deal with implicit flows.
Implicit
tainting.
flows.
Yeah.
Actually, we depend on the precision of tainting. And yes, we didn't consider implicit data flow because we can adopt other security mechanisms on the server. Because we use tainting to track the data flow of core data on the trusted node, right? And the application must be trusted. If there are some malicious code there, the server can use other mechanisms to check whether there is an implicit flow there. Basically, the answer is we don't do it now, but it can be done in our framework.
Okay, I see, but you do assume that basically you have an attacker that could install or modify existing applications, right? So the applications could be malicious?
Yes, could be
maliciously modified?
Yes, yes.
Okay. Thanks.
Just a small question. Thanks for the interesting work. But at the beginning of the presentation, you said that you have some secrets on the device to be protected. How the credentials to access the core while the trusted device are not secrets? Because basically, you should have credentials to be able to access the secure place. So do you have a secure place to access the secure place?
I'm sorry, what?
How about the credentials to go to exchange with the secure place? I don't remember the name you give them, but like the PC at home or something. You must have credentials on the phone.
You mean the trusted node, right?
Yes,
Are you talking about the security of the trusted node?
The security to access the trusted node, like the credentials or things like that, because you must have some certificate which is in memory, so you can have the attacks on memory and things like that. Okay, let's do it again. On your first slide, when you tackle the attacks on the Android data, private data, you said that there exists a lot of attacks to retrieve passwords, certificates, and stuff like that, right?
Yes, many data residue in the memory, yes.
Yes, so when you access the secure place, you must also have some credentials. So how do you prevent this secret to be stolen from the phone?
I lost here.
What are the credentials?
Sorry.
You must give some credentials to the remote server.
You mean the connection between the phone and the trusted node, right?
Yeah.
And how can I prove I am the owner of the phone? Right?
Yes, for instance, because one could say that the bank is a trusted place, for instance, but still you want to prevent this.
Yes, actually, this is a good question, and we think that we have two. Actually, we consider this problem, and we have discussed this in the paper. And we show that the first solution is that you can use the connection between the phone and the cloud. The trusted node are actually independent between the connection between the phone and the Facebook web server, right? And there will be no critical data sent between the phone and the trusted node, because the trusted node will never send the critical data back to the phone, right? So, in our last slides, we show that we do not, We do not. Sorry. We do not know who is using the phone, actually. And we do not protect impersonation in this work.
Okay, that answers. Thank you.
Okay.
Any more questions? Yes.
Okay. Hi, Bill Belowski from Microsoft Research. I'm going to try to follow up on the last question. How is it that the trusted node knows that it's talking to the phone and not to some, not to my phone as opposed to your phone?
We think this is supposed to be used other authentication mechanisms. For example, use a certificate or things like that.
Okay, so there is a secret in the phone there is a secret in the phone that's used to identify it to the trusted node.
But this certificate is.
It won't let you get the passwords, but it will let you use the passwords.
Yes, this is called the password the core abusing problem.
Okay.
And currently we think we need other mechanisms to prevent such abusing.
Okay. All right. Thank you.
Okay, thank you.